If you've ever looked at a weld and wondered, what exactly am I looking at, this video is for you. Today we're breaking down every single part of a weld, what each component does, and why it matters. Whether you're brand new to welding or just want to sharpen your knowledge, stick around, this is going to be super useful. Before we get into the parts, let's make sure we're on the same page. A weld is a fabrication process that joins materials, usually metals, by causing fusion using heat, pressure, or both. The result is a weld joint, and that joint is made up of several distinct components. Understanding these parts isn't just academic, it helps you diagnose problems, read welding blueprints, and produce stronger, cleaner welds. Let's first understand what a weld actually consists of. A weld joint is the junction where two or more pieces of base metal are joined together using fusion, pressure, or both, typically with the addition of filler metal. ASME Section IX recognizes 5 basic types of weld joints. Number 1, the butt joint, where two pieces are aligned in the same plane. Number 2, the T-joint, where one piece meets another at a right angle. Number 3, the corner joint, at the outer edge of two pieces forming an angle. Number 4, the lap joint, where two pieces overlap. And number 5, the edge joint, used on parallel or nearly parallel members. Each of these joints can use groove welds, fillet welds, or a combination of both. Now let's zoom into the most important weld type in ASME work, the groove weld, and identify every single part. Starting from the base metal, here are the key components. Root, this is the bottom-most part of the weld joint, the deepest point of the groove. In a pipe weld, this is the most critical pass because it's the first layer deposited. Root opening, or root gap, the space between the two base metal pieces at the root before welding. ASME specifies this precisely in the WPS. Root face, or land, the flat portion of the prepared edge at the root. It prevents burn-through during the root pass. Groove angle, the total included angle of the groove formed between the two base metals. A wider angle means more filler metal required. Bevel angle, the angle of one prepared edge measured from a line perpendicular to the surface. The groove angle equals twice the bevel angle for a symmetric V-groove. Weld face, the exposed surface of the weld on the side from which welding was done. Weld toe, the junction between the weld face and the base metal. This is a common location for toe cracking. Weld root, the points at which the back of the weld intersects the base metal surfaces. Throat, the distance through the center of the weld. For a groove weld, the effective throat is the depth of fusion. Now let's look at the fillet weld, the most common weld in fabrication. A fillet weld joins two surfaces approximately at right angles to each other, like in a T-joint or lap joint. Key parts of a fillet weld: leg, the distance from the root to the toe along the base metal surface. A fillet weld has two legs, ideally equal in length, forming a 45-degree face. Theoretical throat, the perpendicular distance from the beginning of the root to the hypotenuse of the largest right triangle that can be inscribed within the weld cross-section. For a 45-degree equal leg fillet, throat equals leg guna 0.707. Actual throat includes the convexity or concavity of the weld face. ASME section focuses heavily on throat size in weld acceptance criteria. Weld size, equal to the leg length for equal leg fillet welds. Convexity, concavity, if the weld face bulges outward, it's convex. If it curves inward, it's concave. Excessive convexity creates stress rises at the toes. Beyond the visible weld bead, there are 3 important zones every inspector and engineer must understand. The fusion zone, also called the weld metal zone. This is where the base metal and filler metal have completely melted and fused together. The chemical and mechanical properties here are a mix of both. The heat-affected zone, or HAZ, this is the area of base metal that was not melted, but whose microstructure and properties have been altered by the heat of welding. The HAZ is critical because this is where many weld failures, like hydrogen-induced cracking and liquation cracking, originate. The base metal, the unaffected parent material beyond the HAZ. Its properties remain unchanged by the welding process. ASME Section IX requires that welding procedures are qualified to ensure the properties of all 3 zones meet code requirements.